So if you remember, this is the type of encoding we have. We have single photons encoded in these path states. So for example, state 2 here means that I have one photon in spatial mode 2 in this direction, and 0 photons in the other. You can create general states like this. This is something that's really common, for example, in integrated photonics and also in fiber optics. So it's a really general use kind of coding. And the way we use it with the multi-core fibers, of course, is like this. So if the photons so this state 2, meaning the photons in mode 2, would be the case when the photons here in core 2 of my fiber and there's 0 photons in the other cores. So as I mentioned last lecture, we're interested in these multi-core fibers because they allow us to send, well, these encode qubits or even, say, 4 or higher dimensional systems, all in the same fiber using this path encoding. And of course, it's better, this is more interesting with the multi-core fiber versus using, say, 4 individual fibers because it's more stable. Last lecture, I also told you about some devices we have which make things a lot easier and very kind of plug and play, let's say. One is the multiplexer or demultiplexer, which couples single mode fibers to the multi-core fiber. And so with this, we can connect the multi-core fibers to kind of any device that works with single mode fibers. So our detectors, phase modulators, whatever you want. The other device we have, which is interesting, is this multi-core fiber beam splitter. So this is a multi-port beam splitter, meaning there's more than 2 inputs and more than 2 outputs. This is a picture of the 4x4 beam splitter. We also have 7x7 beam splitters in our lab. And so the 4x4 beam splitter, because of the symmetry of the cores and so on, a typical tomographical estimate of the unitary operation corresponding to this beam splitter looks something like this. And then you can see by searching for the, say, closest convenient theoretical matrix corresponding to the experimental ones is like this. So these devices are very well approximated by a real Hadamard matrix 4x4, which looks like this. So of course you can use this beam splitter to create superposition states, measure superposition states, and so on. As I said, yeah, so this is an example of a multi-port beam splitter. And so I showed last lecture how you can construct arbitrary d-dimensional unitary operations using 2x2 beam splitters, and it's kind of an arrangement of them. You can do the same with these multi-port beam splitters. So there have been a number of art papers that have talked about this and studied this. And basically, if you want to go from, say, like a computational complexity type point of view, if you have d-dimensional multi-port beam splitters, you need less of them to construct your arbitrary unitary, as opposed to the case if you have 2-dimensional beam splitters. So the scaling goes as d squared when you have 2x2 beam splitters. If you have d-dimensional beam splitters, you have a linear scaling. So that might be interesting. It might not. I don't know. So this is the kind of, say, arrangement you could build with these beam splitters and phase shifters to make an arbitrary unitary. So this is, of course, somewhat interesting in practice, but also mostly interesting from theory in the sense that you can kind of do some sort of accounting of how many operations you have to do, and you can always decompose any unitary into some arrangement with your beam splitters. Yeah. So I told you in our lab we built this interferometer a couple of years ago. It's still working operation in our lab. It's a general prepare and measurement device, so we do some state preparation here. The measurement station is here using beam splitters and phase shifters in the preparation, and then beam splitters and phase shifters in the measurement. This particular device is built with a weak coherent state input. We also have other devices that work that we can couple single photons into. We do active phase stabilization, and that's, even though the multi-core fiber is fairly stable, it would still require some active phase stabilization. But as I mentioned last lecture, there's no way to modulate the phase between the different cores rapidly inside the multi-core fiber. So in order to do fast change base measurement and preparation and measurement bases quickly, we use telecom phase modulators, which are compatible only with single mode fibers, not yet with multi-core fibers. So we have to couple out of the multi-core fiber into the single mode fibers to modulate in the state preparation, and then we do the same in the state measurement. So all of our, with this, then so even with this setup, coupling out of the multi-core fiber, we still get really good interference visibility. But to do that, we have to stabilize the interferometer, so we do with a feedback algorithm. And so when the device is left on its own, the count rates at 4 detectors oscillate wildly, and then we can turn on the stabilization and basically stabilize the phase at some value that we want. So they call this value here 0, such that all of the light goes to one of the detectors. So when we do experiments, we first stabilize, and then in some region of stabilization, we apply the phase modulation we want, and we do our experiment. So the device is always stabilizing itself, measuring, stabilize, measure, and back and forth. And so kind of, as you'll see shortly, how many measurements you can do per second depends on how much noise there's in your system, right? And that can be relevant in, say, if you want to do a real protocol. So the idea of this device is that then, so I have this state preparation measurement. Now I can plug something in here in the middle, so I can prepare a quantum state, send it into some channel or circuit or whatever it is I want to do, and then I can measure it, right? So this is kind of the idea here. Let's put something interesting here. So at UDEC in Concepción, we have actually a multi-core fiber with a cable, right? A fiber cable connecting the physics building to the engineering building. It's so this is 1.3 kilometers round trip. So it's, I guess, 700 or almost 700 meters of fiber stretched between the two buildings. Inside this cable, there's actually 2 multi-core fibers and 6 single-core fibers of different types. And we also have a fiber section that goes from the 2nd floor of the physics building to the 6th floor and back. So the idea here is we have kind of like a test bed for, say, like quantum network kind of things in this multi-core fiber. The reason it goes to the engineering building is because our collaborators in the electrical engineering department use this fiber also for their studies in terms of telecommunications purposes in multi-core fiber. So it's in terms of so this is actually installed within the campus. It goes underground, crosses several streets and so on, goes to the middle of the square of the university. So the first thing you do when you install something like this is you see, well, how, does the light actually make it to the engineering department? How are my losses and so on? And we have quite a bit of loss, like almost 10 dB of losses in both sections, right? So it's not a loss that necessarily comes from the propagation distance. I mean, this is very short. It's only a kilometer or a few hundred meters. The loss should be pretty much negligible due to just propagation within the fiber. The reason we have such high losses is all the connectors and the splices that had to be done when the fiber was installed. So because this is specialty fiber, when you hire a company to install a fiber, they don't know how to splice it, right? And also they don't know, maybe they don't know how important it is to not cut the fiber, right? So our fiber has several connections here, which actually are splices, right? But because it's now a structured fiber with 4 cores, so imagine you have these 2 pieces of fiber with 4 cores, and you have to splice them together to optimize transmission, not just in a single core, but now in all 4. So you have all these different degrees of freedom of tilt, of how much the fibers are rotated one to another, and so on. So it's actually quite challenging to have good splices in this type of fiber, and that's why the losses are so. In fact, the company that installed the fiber, they didn't have the machine necessary to do the splicing. Some of the engineering students did the splicing. So yeah, so they were underground doing splices in the fiber to have it installed. There's also quite a few like actual butt couple connectors, like the standard FCPC connectors in the physics building, engineering building, and that of course introduces quite a bit of loss. But the loss isn't actually such a big deal because when you do, well, for many experiments, I mean, so 10 dB of losses is actually something like would be equivalent to, say, 50 kilometers of propagation in a high-quality fiber. So in this way, you can kind of simulate longer distances because you have a lot of loss. So if you do an experiment that has, like device-independent QKD, where you cannot have hardly any loss, it's bad. But if you want to simulate something more real-world, it's actually kind of good that there's a lot of loss because it's as though you have an extra 50 kilometers of fiber here in the middle that's making you lose your photons. So this is what we have and what we're working with. So the first thing we wanted to do was some QKD types experiments, right? I don't know if someone in the school talked about QKD at all, what it is. Does everyone know what it is? Okay, okay. All right, well, I have 2 quick slides just to say what it is, right? So, I mean, the idea of quantum key distribution, just as the name says, so people talk about quantum cryptography. It's not quantum cryptography, it's quantum key distribution. The idea is that you can use quantum physics to share a key between 2 users, right? So in classical cryptography, you have this protocol called the one-time pad, which is also known as the Vernam cipher, which is very old, which around 1950, Claude Shannon showed that this one-time pad cryptography scheme is completely secure from an information theoretical point of view if the 2 users have a secret key that they can use to encode and decode the message, right? So this is one-time pad is interesting because there's a mathematical proof you can use to show that it's secure, which that's kind of rare in classical cryptography. You actually have a proof based on say fundamental principles. But of course, in there you assume that each user has a random and completely private key, right? So so the important thing with that work of Shen is basically reduce the problem of how do I cipher my information. Now the problem is how do I share the key, how do I generate a random key, completely random, and how do I share it between the 2 users, right? I mean, if I want to send a message to one of you, we could meet in person, we could flip a coin a bunch of times, write down the results, separate, and then we could communicate. But of course, that's not practical in any sense. So, so this is the importance of the one-time pad from this conceptual point of view. Nowadays, similar types of ciphers are used. I mean, when you connect to the internet and you see HTTPS, it's using a cipher like this, but it's using most likely AES, which is the Advanced Encryption Standard, which is something similar, it's just more efficient in how it works, right? But it's the same kind of idea. So the question then is, so how do you distribute this key? And of course, quantum key distribution is a possible solution given by quantum mechanics, and it's based really on the fact that, well, quantum physics has kind of inherent randomness built in, right? When you can do a measurement such that the output is completely random, and also you can encode information in such a way that a person cannot access all of the available information. So the access to classical information that you encode in a quantum state is limited, right? And so just the basic idea of how it works, this is, I mean, a picture representation of the BB84 protocol, which is just kind of the simplest example. So basically, user A is going to choose 2 random classical bits and encode them and associate each value of these to 4 quantum states, and these are non-orthogonal states. So that might be the 2 eigenstates. So for example, if the, so I drew this kind of poorly. Let me take advantage, there's a blackboard here. You might say, okay, if I have the Z basis and the X basis, and you might say, okay, if the 2 random bits are equal to 0, 0, I'm going to do that. If it's equal to 1, 0, I'm going to encode this Z eigenstate, so this would be the plus Z eigenstate, the minus Z eigenstate. If they're, let's see, 0, what do I want to do? 1, 0, 1, right? This would be the plus X eigenstate, and if it's 1, 1, it would be the minus X eigenstate. So on the value of these 2 bits, you can encode one of these 4 states, and these are non-orthogonal, right? They're the eigenstates of 2 different Pauli operators. So that's how you encode the information. Party A sends the qubit to party B. Party B is then going to do a measurement in either the X or the Z basis, right? So they measure, they have some measurement results. And so basically, based on, they can then communicate, and they can say, okay, which basis did you encode in? I can say, okay, I measured in the X basis. What basis did you, photon 1, for example, I measured in the X basis. What did you encode in? Oh, the X basis, great. So our results should be correlated, right? Because if prepared, say, the plus X state, I should measure the plus X state, assuming there's no noise in the channel, right? The same thing, if I measure the Z state, I check to see if the Z basis was used to encode. If yes, we keep it. If the bases are different, you just discard the information, because if the the encoding basis is X and I measure in Z, my output will be completely random. So it's just basically, to me, it appears as noise, and so it doesn't transmit any information. So, so like this, you can do this communication after you send a bunch of qubits, and in the end, the measurement results here in party B should completely correspond to at least to one of the bit values, right, based on whichever basis was chosen. So you can think of these two bits as one of the bits determining which basis to use, and the other bit as to which state to encode, either the plus or the minus state, right? So this is kind of the basic recipe, and then of course there's all sorts of analysis that you can do to show security, and there's, I mean, I don't know, 30 years of work in this field. But the main point of why is this secure, it's because, well, the eavesdropper cannot copy the information in this qubit perfectly, because if I measure a qubit, the most I can obtain is 1 bit of information, right? But 2 bits of information were encoded into the qubit, essentially. So if I don't know which basis was used, I can't encode the information, and so this is, prohibits me from accessing all of the information. I can maybe sometimes I get lucky, I might measure in the right basis and obtain information, but a lot of times I will be unlucky. And moreover, when I'm unlucky, I mean, party B is expecting a qubit to arrive, right? So if I measure, I have to remain invisible, I have to send something along to party B. I mean, if I steal a photon here, measure it, I have to then send something, right? Prepare some state and send it along to party B. Sometimes I'm going to prepare the wrong state. And so when A and B are measuring and are preparing and measuring the same basis, I will now provoke the eavesdropper, I will now provoke errors in the results. So I end up, you can see my footprint there, or you can see I was intruding on the system, right? So this is the basic concept, right? And there's lots of different variations and so on. So this is what we want to do in our fiber. And so I showed this picture the other day. This is kind of how it works. So we have the state preparation, so we can prepare states of this form here. So we can prepare different bases by changing the phase here. So this is now in 4 dimensions. So, but still we can have something like an X basis and a Z basis just by changing whatever phases we imprint here using the phase modulators. We send then this photon through the multi-core fiber channel, the fiber. The party B then is going to choose whether to measure in the X or the Z basis by applying some phases here, and then have the 4 possible measurement results. So this is the way this protocol works. So this is the kind of experiments we've been doing over the past, I'd say, year or so. This is part of the thesis of Kei Sawada, who's actually a Brazilian student from Rio, who did his PhD with us. But he, so the point is here, because we want to use the full length of the fiber, and we have this interferometer all set up in the same lab, we do like an out and back type of experiment. So Alice, party A, is here in the lab, prepares the state using the interferometer, which I mentioned. We couple the light back into, or the photons back into a multi-core fiber, which then goes, say, over here, the engineering department. We send it through one fiber and then send it back through the other. I mentioned there were 2 in the cable. So we go out and back, and then the information goes into Bob's measurement device, which is just like this. So there's some other devices here which I didn't mention. There's these polarization controllers, which you have to be controlling all the time so that the polarization is all the same in each core. Another thing we have here are actually intensity modulators. We use that to kind of compensate for different loss levels in the different cores or in the different fibers. But also we use that to do intensity modulation, which is necessary for what's known as the decoy state protocol, which is, I mean, we can get into that if you want, but it's to make the life more difficult for the eavesdropper, you want to send different intensities of pulses. So sometimes you send a vacuum pulse, so you completely block off the channel. Sometimes you send a pulse that's a little bit more intense. Sometimes it's in between, and this makes it harder for someone to steal your photons and remain invisible. That's kind of the basis, the idea of the decoy state protocol. So we use these intensity modulators for that. So this is all computer controlled and happening at around 2 megahertz, so 2 million times per second. And again, as I mentioned, we have this stabilization algorithm working now with the multi-core fiber connected here in the middle, right? I should mention, so, okay, the detectors we're using here are in-gas indium gallium arsenide detectors, which have really low detection efficiency, and in fact, to keep the dark counts as low as possible and so on, they're operating around 2.5% efficiency. So it's really low efficiency, there's lots of losses, and so on, right? So, okay, this is a fun thing to do, right? So here's some results. So maybe this looks a bit complicated. What we're measuring here is the quantum bit error rate. So this is basically how much noise is in your system, how many errors. So if I prepare a state in the X basis, I measure in the X basis, I expect to see the 0 state, let's say. How many times do I see a state that's not the 0 state? So that's the error rate for the X basis. You have a similar error rate for the Z basis, and then you can combine them together and average them if you like to have kind of the average quantum bit error rate. So it's well known so part of the theoretical work in quantum cryptography is to see, okay, what's the maximum Q-bear, as they call it, right? What's the maximum Q-bear allowed for such and such protocol? Or how can I raise the allowable Q-bear and so on? What's the Q-bear for such and such kind of attack? And so one of the big milestones of quantum cryptography was to have kind of an absolute level of Q-bear that was based on, say, the most fundamental physical principles and not on any particular implementation, right? So you have these numbers in the literature and so on. And so one thing that's interesting in higher dimensions, right, is that the Q-bear is a little bit higher. So if you remember 2 days ago, I showed a graphic that showed a Q-bear somewhere around 11% for qubits, right? When you go to four-dimensional systems or Q-quarts, the Q-bear actually increases to something like 19%. So that's one of the advantages of using higher dimensional systems, is you can allow for more noise, because, and why can you do that? It's because if an eavesdropper steals the photon and measures it, right? So say the photon comes and measures it, oh, I obtained 0 in the Z basis. Okay, what's the probability that I send prepare the photon again in the proper state and send it along? It's now, what, 1/4, right? As opposed to 1/2 in the two-dimensional case. So this means that the eavesdropper will provoke more errors when they try to steal and reproduce the photon. And this is true for kind of any attack. I'm giving a simple example of what's known as intercept or send attack, but when you go to any kind of intrusion by the eavesdropper, it's more difficult in high dimensions. So that's one of the advantages of going to high dimensions. But okay, so here's a couple different configurations which we do with different decoy state values and so on. The point is that, let's see, I don't even remember. So we have different, so the point is that we obtain results for Q-bear lower than the threshold for all three kinds of experiments we can do. So one experiment we can do is we can just not connect the fiber in the middle, right? Or we can use just a patch cord, so we're going, say, a few meters only. We can then go up, we can go from the second floor to the sixth floor, which is around 200 meters round trip, or we can go to the engineering and back, which is 1.3 kilometers or whatever I said. So so these are kind of the three, I guess I have this, these are the 3 points. So interesting thing is that we have, let's see, this is what we call back-to-back. So this is just on the optical table. See a few meters of propagation. This is when we have, I guess, okay, sorry, these two results are when we go 200 meters or 1.3 kilometers. And then these results here are when we do the back-to-back, but we use attenuators and we really force some losses, so to kind of simulate a longer distance. And so, yeah, in general, the interesting thing here is we're able to run the system and have a error rate that's low enough that we could actually do QKD. Of course, all these measurements I'm going to show you here is sort of benchmarking this fiber and this system for QKD. We don't actually do QKD in the fiber yet. That's one of the next steps. These are some results then showing, okay, how many secret bits can you establish per pulse of light that's sent from the transmitter to the receiver. So you have some values like this. And so you can see that it's quite low. I mean, best case scenario, I mean, roughly, say, 10 to the minus 4, 10 to the minus 5. So the repetition rate is 2 million times per second. So we're sending a few tens of bits per second. It's very low. It's not good. But this is kind of the curse of QKD, right? This is something that's really common in many experiments. Of course, our repetition rate is quite low, only 2 megahertz. Many experiments operate at 1,000 times faster, which is also something which we're working on, is speeding this up. But the interesting thing here, basically the benchmark we wanted to do is, okay, how far of a distance will our system allow? And so we can see if in a perfect situation where we have, say, low losses in our fiber, we could go around 100 kilometers, which is more or less this 20 dB of loss here corresponds to about 100 kilometers of propagation in a fiber. So again, part of the reason this number here, the secret bits per pulse, is so low is because we have these, let's say, crappy detectors, right, with very low efficiency. So the first thing is, okay, we can improve the detectors. So we actually, in our lab, more recently, we have these high-quality superconducting nanowire single photon detectors. So we did experiments connecting those detectors as well. So this is kind of some of the old results here in yellow. And so you can see that these higher quality detectors, basically the efficiency is much higher, probably somewhere around 50, 60%. I don't know off the top of my head. But you can improve the bit rate by, I guess, 2 orders of magnitude. So the key rate, rather, by 2 orders of magnitude. So with this, if you kind of fit this data to the known theoretical curves, you could probably go around 150 kilometers. So yes, I should mention there's several. Well, Kei Sawada was the student who did a lot of this work as part of his PhD. Nelson Villalba is working on this right now, and Gustavo Santos is a postdoc. He's actually from Paraná, and he's there with us working in the lab. And so actually these results, though, again, it's a real low key rate and so on, these we're fairly excited because basically we're right around the threshold of breaking the key bits per pulse record for decoy state QKD, right? And so this is, again, so these numbers look really low, but it's kind of everybody's numbers are really low and really close to breaking the limit. And this would be really cool to be able to do because the reason we're able to encode more is not because we have better technology necessarily, it's because we have, say, this 4-dimensional system, right? So, of course, you know, when you have 4 dimensions, you can, in principle, establish 2 bits per pulse, right, in principle. So that gives us a little bit of an advantage. Yeah. It's kind of some more technical details, so, which I think are interesting. So one thing we did is, so as I mentioned, we have this stabilization algorithm, right? And so you can kind of decide, well, how much do I need to stabilize, right? Because if I could put my threshold really, really high, you know, so that I'm, you know, have really low noise, but then if the threshold's really high, I'm never going to measure, actually. I'm going to be stabilizing all the time. So you say, okay, well, I'm going to lower the threshold. I'm going to say, like, okay, when it's pretty good, do a measurement. I can say, okay, only do a measurement if it's excellent, or I can say, okay, if it's pretty good, do a measurement. I'm going to do more measurements, but I'm going to pay a price of lower fidelity, right? So here's some, so we kind of set this threshold a certain way, and I guess this here is probably a threshold of maybe, I think it's 90% roughly. So, which is basically saying, okay, when 90% of the photons go to detector 0, I'm going, and so I say 10% noise, I'm going to say that's okay, and I'm going to do my measurements. So here's like what when you actually go and do a measurement, this is the state fidelity that you obtain for those 3 different configurations I mentioned. So if we either go back to back in the lab, or we go to the 2nd floor, or we go to the engineering department. And so you can see they're more or less well, here's the values, right? The mean of these fits are more or less the same. I mean, there's a little bit of a difference. And actually, you see a kind of a big drop-off when you go from, say, 200 meters propagation to 1.3 kilometers propagation. And the other thing, you see that the curves get a little bit wider. The standard deviation is a little bit wider. So, so this is important for a couple of reasons. One, it's good. You need to know how this works in order to set your threshold and so on. I mean, it's not trivial. Maybe it's better to, I mean, which is better, to measure more or to have higher fidelity? I don't know. I mean, we should probably do some calculations to kind of try to optimize this, and that's kind of something we've been discussing. But another thing important here that this shows is if you go to, I mean, every theoretical paper on QKD, it's always assumed that the noise level in the channel is constant and does not depend on the propagation distance. So when people do a calculation, they say, okay, I'm going to have 10% noise, but then okay, now I'm going to go, you know, 10 kilometers, but I'm going to go 1,000 kilometers with this 10% noise. This isn't true. You have, I mean, the noise increases with the propagation distance, right? And our data shows this, right? The fidelity is slightly lower for 1 kilometer propagation versus the other one. So this is, you know, an example that this cannot be a static parameter that you kind of throw into your model. It has to be something that depends somehow on the physics of the system you're using or considering. So, yeah. So that's one thing we did. So then the idea is, okay, well, how stable is the system over time? So here's kind of showing you so this is the kind of measurement everyone loves to do. Align the system, press go, and then go home. And then, so this is the system running basically overnight in the back-to-back configuration of the lab table. You can see that the fidelity, so the quality of the channel is really high, for 16 hours, well above the fidelity limit that you need, which is somewhere near 80-something%. But when you go to this 1.3 kilometer link, the fidelity, well, it oscillates a little bit more, but it's also starts to decrease below the limit after, say, 10 or 12 hours in this particular system. So, I mean, the reason that is because you have, say, polarization drift and so on, which, I mean, if you have a fiber now going under the campus and going through several different, say, temperature regions and so on, and it's going inside the building, outside the building, under the ground, and so on, the polarization in the four fibers, and the four cores, rather, start to change independently, and then you start to lose some of the visibility, or some of the overlap, right, or some of the, let's say, indistinguishability of these modes. So, so that starts to decrease this. So this, shows us that, okay, if we want to do something over a long distance, you have to include some polarization compensation in your system, right? So this is kind of an important thing to know. And so if you're only working in this kind of scenario, assuming, even if you took a whole roll of fiber, put it in the lab, connected it, you would probably see something fairly stable because it's a really controlled environment. When you go to the uncontrolled environment, you have the noise. So this is something else we learned from this. Okay. So now I wanted to switch topics a little bit and actually go to a topic which I spoke about yesterday in the colloquium. I'm going to repeat myself a little bit here, but I also kind of prepared something that's a little bit distinct, so bear with me if you were at the colloquium yesterday. So I mentioned this paper, or this work we did on POVMs using multi-port beam splitters, in fact, the multi-core fiber beam splitter. And what I kind of emphasize as much in the colloquium, which I want to emphasize here, is this is kind of a new tool in the toolbox, right? So this is basically, these multi-port beam splitters are like plug-and-play POVMs, right? So and I'll say more about that in a minute. So what is a POVM? So it's a measurement, so it's a set of measurement operators, right? Such that they're positive operators, and they sum to identity. So basically, they can be projective measurements, but they're not necessarily all projections onto a set of orthogonal states, right? So I can have, say, more measurement operators than the dimension of the system that they act upon, for example. They're important for many things, in particular quantum state discrimination. You can generate randomness with them. You can use them in QKD and so on, different protocols. And so how do you implement them? Well, you can use this result of this Naimark dilation theorem, which basically tells you that any POVM on a given Hilbert space of some dimension can be realized as a projective measurement on a larger Hilbert space. So the idea here is that you want to implement, say, this operation, right? Applying this particular measurement on your state, which is non-orthogonal projectors. You can realize this by doing a projective measurement on a larger system. So in practice, how has this been done in the past? So this is a paper by which was done in Concepción before I was there, and some other collaborators. And basically, in this experiment, what they had to do was project onto so this is a qubit, this is actually a polarization state of photons, and they define these three non-orthogonal states here, which are given here below. So you can see they're non-orthogonal. How do you do this in practice? Well, okay, there's no polarization device that you buy that does this, right? You have to build something in the lab. I mean, a polarizer splits, H from V or something like that. How do you do this? And so, again, the polarization space is only two-dimensional, right? But now I have three states. So how do I do a measurement in this three-dimensional space? So you have to find some, first you introduce an ancilla, which can be another degree of freedom of the photon, for example. And then you have to apply some device, right, which is going to represent as a unitary operator on these two systems, right, system and ancilla, which is going to evolve into some psi k here, such that, psi k, okay, such that these psi j or psi k states, system ancilla states, are now associated to the higher dimensional projection operators which you need to implement. Right? So the big question is, okay, what is the U necessary such that I can do this transformation from these three states into set of orthogonal projectors. So these states here, I should mention, are orthogonal. So when K is different from J, if you do the scalar product, you get a Kronecker delta. So how do you do that? Well, okay, so for this particular configuration, there's, say, you can think of a quantum circuit that would do this. So this is kind of the quantum circuit representation of how you do this. And then, but in practice, you have to build an interferometer. So this is what they did. In fact, this is still set up somewhat in our lab. I think Felipe worked with this setup. It's basically, this is a double Sagnac interferometer. It's basically just like any other interferometer, but it's more stable because both paths follow the same route. So one path goes counterclockwise and one path goes clockwise. So it's all the same mirror. So if a mirror vibrates, both paths feel it, it's more stable. So the point here is that here, these different operations here, these rotations are corresponding to wave plates, and the PBS, this is a polarizing beam splitter. This is like a C0 gate between the polarization and the path. And so you can basically map this circuit here to this operation, and then you can have 3 detectors which, you know, if one of the detectors makes a click, you know you detected one of the 3 states. So this is how you do this in practice. So this involves, building an interferometer, and so when you have an interferometer, now you have to make it stable, and you have to worry about the overlap and all this kind of stuff. So it's something you can do, but it's not, say, plug and play, right? It's not, a simple polarization measurement is I take a beam splitter or a polarizing beam splitter, I put it in front of my beam, and maybe I have a wave plate that I might turn. It's really, simple to do. Here, it's quite a bit more involved. So on the other hand, in which we did in this paper, is we did this POVM measurements, but using the multiport beam splitters. So that's what, and it's plug and play in the sense that all you do is connect the multiport beam splitter to your system. And so that's what I really want to emphasize. And so the basic idea, it's more or less what I described, right? You use this Naimark theorem. You say, okay, well, if I have a unitary operator of dimension large d, and I have some Hilbert space of some smaller dimension, lowercase d, and then I introduce some ancilla modes here, right? Well, then this quantum system here in lowercase d is going to evolve through this, and I'm going to have uppercase d possible outcomes, right? Each of these states corresponds to a pure state in principle, but it's a set of non-orthogonal pure states because there's uppercase d of them, and this thing is acting on a Hilbert space of dimension lowercase d. So the point is, my photon enters here in these modes, and these are just vacuum modes, which I use for the measurement. So so if you figure, okay, how many different ways can I connect lowercase d inputs in this device? So any multiport beam splitter has this many different POVMs which you could implement. So depending on what the unitary matrix looks like, they can be very different or somewhat similar. It doesn't matter. And of course, this is true for any multiport device. So not just a multi-core fiber beam splitter, but any multiport you could build would do this in this kind of plug-and-play fashion, right? And so, yeah, if I know how do I calculate what these states C are, I basically can back propagate. So each of these wires are like the computational basis. I can basically write the computational basis states in the output and back propagate them through the unitary to see what the POVM elements are. So of course they depend on some subset or some submatrix of the unitary device itself, which we call M, right? So you can figure out what the elements of the POVM are, what your projectors are. So in our lab, as I mentioned, we have 7 core beam splitters, and so that's what we use. This was characterized in the same way that I told you about the other day for the 4 core beam splitter, using the same technique, actually by the same people. And so you have this big matrix here. It's just fairly ugly. There's nothing, I don't know how to describe this in fewer words or fewer symbols than just writing this to you. So, I don't know what it is, but this is what it is. So one thing that was done was, okay, within this unitary 7 by 7, and there's 35 different possible POVMs, which is the most interesting? So the answer, what that question means will be clear in a minute. But so the POVM which was chosen was this one. So it's some subset of this matrix here, and then renormalized. So this is the M operator. And so the question in this paper, which so I didn't talk about this next part in the lecture the other day. The question is, okay, I'm saying that this is not a projective measurement, and the question is, okay, well, how can you show that it's a non-projective measurement, right? This is something that people like to say, I want to like benchmark this and have some threshold and show it's really a generalized measurement. So the way this was done is by inventing a kind of quantum game, right? And so I'm telling you about this because this is sometimes an interesting thing to do. If you want to show some, say, quantum advantage or some sort of advantage, quote unquote, you can kind of invent a game that does that for you, right? So the idea here is that, okay, you're going to have a transmitter, right? So Alice is going to prepare one of 7 different quantum states according to this variable x. They're going to send this quantum state from Alice to Bob. So this is a 4-dimensional Hilbert space, right? So rho x is one of the x states. Bob is then going to choose between 2 different types of measurements, right? One is going to be one of 7 different projective measurements, right? And so these projective measurements are going to have 2-dimensional outputs, right? So the idea is that these measurements are projective, but they're dichotomic, so they're 2-dimensional. And you can do this, I mean, if you have a d-dimensional projective measurement, you can just group the results and make it so you project into different subspaces. I mean, that's not a problem. The other measurement, which Bob can do, is implement the POVM measurement, which of course has the 7 possible outputs. So this game is the guess Alice's input game. So the idea is that Bob wants to guess what the value of x is here, which is what is the input Alice is using. So yeah, you can create some like a kind of score function, if you will. So the way the game works is like this: is if Bob is going to do the projective measurement with the 2 outputs, we'll reward 2 points if the output. If the output is b equal 1. So when b is equal to 1, it means that x is equal to y. So for one of the outputs, we reward 2 points, and for the other output, we reward 1 point. The point system is kind of arbitrary, but this is what was chosen, right? Meanwhile, for the POVM measurement, we'll reward 3 points if the output is equal to the input, else 0 points, right? So you make this game structure, and then you can say, okay, what's the total number of available points? So you can kind of create this score function, which depends on, okay, what's the probability of doing the projective measurement? What's the probability of doing the actual POVM measurement? And you can say, okay, let's suppose Bob's trying to cheat. He's saying, I have the POVM, but he really doesn't have it. He's just kind of saying he does and trying to reconstruct the results just with projectors. And so you can do a bunch of optimization with semi-definite programming and so on, which is what was done with this score function. The details are it's not worth getting into. But you can show that, okay, the upper limit for this score function for projective measurements only is given by this weird-looking number here. And the point is that if you include the POVM measurement, you can obtain a score function that's larger. And so this is kind of the game that was invented to show this, the real, like, the fact this is actual real genuine POVM and not a false, a measurement posing as a projective measurement posing as POVM, if such a thing exists. So this is the experiment. It's, again, the same preparation stage which I've been showing you, right? Again, also with the intensity and phase modulators, polarization control. And then, so Bob is going to switch between 2 different setups, right? One which is just a projective measurement using the 4-core multicolor fiber beam splitter. And then the other measurement is going to use actually the POVM measurement using the 7-core multi-core fiber beam splitter with 7 detectors. So basically the idea here is we're going to benchmark, and so it's like I'm saying to you, I want to prove to you that I actually have a 7-core beam splitter and not a 4-core beam splitter. You can think of it that way maybe. So in order for this to work, we had to have extremely high interference visibility. So those curves I showed you, I mean, we had 0.995 visibility, so near perfect. Which we were able to achieve through, carefully aligning all of the polarization and so on. And so this is just some example of results. So there's lots of results for all the different projective measurements and so on. But you can see that the experiment theory are almost identical because we have such high visibility. And the reason we had to have that is because these are the bounds. So this is the projective bound, which I showed before, 62.51. this is the non-projective bound, so the absolute limit was 62.75, so there's just a little bit of room here. And then our particular experiment, if it were working perfectly, would give 62.69 or 60.7 roughly, and we obtained this value here. And so, I mean, because this is, such a narrow gap here, it's 0.1, let's say, we had to have really high visibility. So this experiment took a while to get it to work properly, but we're able to do that, and this was thanks to these high-quality beam splitters and so on. But the point is we were able to kind of prove this and do this guess Alice's input game and show that it's a POVM. So this is kind of what you do to you propose some experiment, some device, something, and you want to show that it's interesting for some reason. So yes, I wanted to share these details with you and also show you, this idea of, okay, how can I do things? How can I invent games and quantum games or whatever you want to make a point? Yeah. So okay, the time that's left, I guess I want to talk about. So I mentioned quite a bit entanglement on the first lecture, and the second lecture we talked about multi-core fibers. So I want to talk about entanglement in multi-core fibers. So of course you have these channels. I showed you can send approximately single photons through them or weak coherent states. Now we want to send entangled photons. So of course there's many groups working on this. So I chose, say, 3 experiments which I thought to be kind of emblematic of what's being done. So this is an experiment which is, I guess, from 2019 from a group in Korea. So what they did in this experiment was they have this PPLN crystal, so it's a down conversion crystal. They have a pump laser beam, and they send it onto this spatial light modulator. And so here's kind of the 3 regions of these are 4 different things they do with the spatial light modulator. I think the only one we really have to look at is this one that says 4 beams. So basically you can see that there's different grayscale pattern on the 4 different quadrants. And so basically these 4 different quadrants prepare these 4 different beams in these particular points. So they're using the SLM as, say, diffraction gratings, 4 different diffraction gratings that'll take a little piece of, say, a corner of the Gaussian beam and make it into its own Gaussian beam located a certain region. So that's how they prepare kind of 4 laser beams, right, from one. And so they pump the crystal with these 4 laser beams. And so I told you about this, the idea of the angular spectrum transfer. So in SBDC, this is pretty easy to imagine. If I have a crystal, so this is like the front of the crystal. Of course, if in a typical experiment, you illuminate the crystal with a beam, so you know that all the photons are coming from that region of the beam, right? And so the photons are born at the same time, or in the same area, right? Same point. So basically, you know that both photons are going to come from here, or both photons are going to come from here, and so on at the crystal. So what they do is they illuminate the crystal with, say, 4 beams like this, and so you know, okay, well, both photons are going to come from here, or from here, or from here, or from here. You're never going to have one photon coming from here and one photon coming from here because the photons are kind of born from the same pump photon, right? So, so in this way, you have kind of entanglement. If you say, okay, I have an entangled state that is 2 photons from here, or here, or here, or here, right? So, and of course, this looks just like the face of the multi-core fiber that's right here, right? So, with this, they have these photons being born in the same part of the crystal, and then they couple the light, so they have actually 2 different beams. So the green ones here are below, propagate in this direction, and they couple them into the multi-core fiber, and then the other photon, so photon 1, photon 2 propagates this way, and they're able to couple it into the multi-core fiber. So again, this is kind of kind of direct coupling. It's like brute force, if you will. You have low efficiencies and so on, but they were able to do it. And then they couple out of the multi-core fiber, and they use these same spatial light modulators to do the measurements, because the idea is you want to change the phase between the 4 cores or the 4 regions. So they use the same kind of thing. They imprint a different phase in each of the quadrants, and then they're able to do measurements. So yeah, so this is the basic scheme. So yeah, this is kind of one of the first experiments back in 2019. It's really kind of, it's proof of principle. But still, they were able to have pretty good results, and they violate kind of generalized Bell inequalities in higher dimensions, so not just dimension 2, but dimension 3 and 4, which is why they have different masks here. Yeah, so this is a pretty nice experiment showing this. So the fibers here are not, I mean, it's a few meters of fiber. I don't remember, but they're not propagating over any real long distance. But this is what they did. So, and so this is fairly similar to the experiment I showed you of QKD, which was done in Concepcion a little while ago, or back in 2017, in which you basically by brute force couple light into the fiber. So in our lab, right around when I arrived there, we worked on an experiment trying to improve this a little bit. So what we did is, so here's our experiment. And so here, this is the nonlinear crystal. So we use the same kind of idea, and here it's kind of drawn out. So again, we illuminate the crystal with 4 regions, and we know that, okay, both photons are born in the same region. And then we're going to, again, map these regions onto the multicore fiber and couple the photons into the fiber, just like they did, right? The difference here is that the way we prepare these regions is we take our pump laser, we couple our pump laser into, with a demultiplexer, which is this, into a multi-core fiber beam splitter, and we basically divide the pump into 4 regions, right? So it's all fiber-based. We don't have these SLMs and so on. So then we have the multi-core fiber, so then we have a multi-core fiber cord, which comes here, and then we have some free space because of the crystal, but basically we have the face of the multi-core fiber being mapped onto the crystal, and then it's being mapped back into the multi-core fiber. So it's kind of a little bit more integrated in that sense. It's also, in principle, you could change, without changing the source, without changing either the optics here, you could change from a 4-core fiber to a 7-core fiber, whatever you want, so it's kind of nice in that regard. We didn't do that, but in principle, you could. Yeah, so we have the photons then propagating here through the fibers. Actually, both photons are always in the same core. And then we did some measurements by 2 different measurement schemes. One of them is just like is basically a direct measurement, so you can see, okay, what's the probability to see both photons in the same fiber. And then another measurement scheme is you can actually use a beam splitter, and you can send these photons onto the beam splitter, separate them, and you can look at different coincidence counts and so on. So you can measure in different bases. And so that's what we did. So we measure in, say, at the computational basis, and we measure in a superposition basis. We obtain some results, and we're able to actually show that we actually do have, say, higher dimensional entanglement. So higher than 2-dimensional entanglement with these results. They're not very particularly good results. You see we have lots of errors and so on, and this is just because we didn't control the phase at all in the experiment. So we're kind of, going on luck to measure, and you're trying to measure, and the phase is drifting, and you're kind of just dealing with it. We also were able to violate some quantum steering inequalities. So this is the kind of inequality we tested, where P and Q here would be like, P might be measurement on a computational basis, and Q is measurement in different superposition bases. So, and we're able to see quantum steering for different combinations and so on. Yeah, so this was a pretty good source. It has, several different problems and so on. One thing we did do is, so as I mentioned the stability, so we actually, measured, okay, how stable is the source, and it's stable over the scale of a few minutes. So basically, when we align everything, we knew we had a few minutes to do some measurements, and then it slowly was getting worse and worse, and then we would have to stop. So this was more or less the idea of this experiment. So of course, this is a pretty good source, but to make it better, you have to have stabilization, and basically take all of this stuff, all these kind of technical issues for the single photon experiments, adapt them to the 2-photon experiments, which is a little bit more difficult because, of course, all of the phases and counts you have are now in coincidence with 2 photons. So if you want to have your kind of, how good is your stabilization algorithm depends on, well, how much, or let's say, how intense is your feedback beam, you're doing a measurement of the phase, right? So you kind of get in like a quantum metrology kind of question. How well can you estimate a phase with a certain number of photons, maybe a few thousand? Okay, I can do it pretty well with, say, 10,000 clicks. Okay, but now I need 10,000 coincidence counts in order to do the same in the 2-photon experiment. Plus, and so that's a little bit more challenging. Also, the phases, because now you have sometimes 2 photons in the same fiber, the phase oscillates twice as fast, which is the idea of quantum metrology, that if you have more photons, you have more sensitivity to the phase for measurements, but now it's also more sensitive to the noise. So there's like some trade-off. But this is something that we're kind of in the process of getting working, having the stabilization with this. So the other experiment I wanted to mention to you is this one here. So this is a little bit different. This is the idea here is they used the multi-core fiber to distribute polarization entanglement. So this is actually a 19-core fiber. It was actually 411 meters long. And so what they did here is they down conversion source. So light is coming out here in this kind of Gaussian region here. So this source, it's actually not just a crystal, it's an interferometer and so on. But so the point is that the photons that leave here are polarization entangled and also momentum entangled, so they're going in the same directions. And so the idea is that, well, the photons are always going to arrive in opposite, diametrically opposite regions here on the face of the fiber. So they should go in kind of through opposite cores, right? And so they showed that here. For example, this is an example of photons arriving. So they have one detector looking at photons going through core 1, and they say, okay, how many times do I see the photon pair or the other photon in any of the other cores? And so you can see that, well, when the core is 1 prime down here, that's where you have a lot of counts, and for the other ones, you have really low counts. So they have low crosstalk. So basically, I know that if I look at 1 prime, I'll have a photon pair that are in principle entangled in polarization. If I look at, 2 prime, I should also have a different pair entangled in polarization. So this really is like multiplexing of polarization entanglement through the multi-core fiber, which is really cool. So you have, and actually, I mean, in principle here, you could have, say, well, I guess we have the center core. So I mean, in principle, I guess 9 channels, right? If you have all the pairs. Yeah, so it is, I mean, a way to kind of to take advantage. So typically in an experiment, you would maybe put a single mode fiber at or put 2 single mode fibers, 1 at each region here of the down conversion source, perhaps. Here you actually you're taking advantage of all the light that's coming out of the fiber. And you have these different channels, and you can send them to different people or whatever you want to do. And yeah, and so what they showed is that over 411 meters of multi-core fiber, this low crosstalk maintains low, and they're actually able to have really high polarization visibility. So they do these experiments here, which are like 2 photon Malus experiments. I put 1 polarizer and one of the photons at some angle. I rotate the other one, and I see some nice curves. And so then you can change this polarizer to some other angle, do the same thing. And if you can see high quality curves in, say, 2 mutually unbiased bases, which is what they did here, then you kind of know you have good entanglement, and probably, I mean, they do in the paper show some calculations of entanglement witnesses or Bell inequality and so on, and they have violation. But in practice, it's like this. So these results, again, are for, say, two opposite cores. So these are 2 opposite cores in the inner circle, and then these are 2 opposite cores in the outer circle. So this is pretty nice experiment. Yeah. So let's see. How am I doing for time? So I'll just mention one quick thing, and then I'll skip something that I was going to say. So, of course, I already mentioned this 2 photon interference. And so, of course, something we did a while ago back in the beginning was to check 2 photon interference in multi-core fiber beam splitter. This is something you can do, and is something that's important for many different protocols, and even for, like I said, measurement device independent QKD. So because of this high quality interference character isn't just true for single photon states, it's also true when you have 2 photon interference. So we do this, you can actually do this with the weak coherent pulses, which I've been talking about, but you have to make them incoherent. So you have to basically take a laser beam, split it in 2, and then delay one of the pulses in relation to the other by a distance that's greater than the coherence length. And so when you do that, you no longer have single photon interference or first-order interference. You only have a second-order interference, which is photon-photon interference. So you can see this kind of Hongel-Mandel dip. So this is a dip in the coincidence probability. And then, so in some of the outputs, so here's all of the possible 2 detector outputs. So I can look at, say, output in red hour with red hour, or blue with blue, or one of the reds with one of the blues, and so on. So you have 6 possible outputs. So these are the curves. So you see 4 curves are dips, and 2 curves are peaks. And the reason the dip is not so deep, let's say, is because it's a weak coherent state. You have some noise that comes along, which are these components here. So if you think about the input state, you say, okay, I'm detecting all these coincidences, so I'm seeing 2 photons. I'm going to pretend there's no such thing as 3 photons, or they're really improbable. What are the different ways that 2 photons can come from these 2 pulses? Well, you can have it that 1 photon comes from each pulse, or you can have 0 photons from the first pulse, or first beam, second from the second, or vice versa. And so these 2 events here don't contribute to this interference, only the third term. And so that's why the visibility is reduced. But still, you can calculate what the limit is, and you can use this to benchmark your system. And actually, this is exactly the kind of thing you do in MDI QKD. So, so we're basically at the end of the school. I'm going to skip something here and just move on to something else. I was going to tell you about quantum discord and so on, but I think I'm going to skip that and just go to what are we working on now, what are the challenges, and so on. So, yeah, I mentioned, so we've done this benchmarking of the multi-core fiber system for QKD. So now we just got a project approved last week. And so we want to do actual QKD, like full stack QKD, meaning not just distributing the key, but actually using the key to connect, 2 firewalls or whatever you want. So actually connect IT equipment using the system such that you can not just distribute a key, but also use it to do something. So make a VPN with quantum keys. And of course, to do that, one of the things we're planning on doing this project is to integrate the multi-core fibers with, say, chip technology. So having source and receiver on chip. Yes, that's one of the main goals, and I think other groups are working on this as well. I mentioned the fact we have to control the phase and the polarization. I actually mentioned that Aderis, my student, he's been working on this. And so actually, I showed you some results. Here's some even better results, which he obtained, which shows even better oscillation. So we're playing around with some ways to control the phase or the polarization without having to take the photons out of the multi-core fiber. So this would be great if we could get this to work. Even if it's slow, it will still help us with stabilization. Because again, if we are all in multi-core fiber, it should be much more stable. So we're working on this. As I mentioned, also these multi-photon states and interference. So the idea is now we have this cable in the campus, we have entangled photon sources, and so we want to do Bell inequality experiments at distances and so on, create 4 photons, interfere them, the beam splitters, things like this. And so Leticia, who's here, right over here, she has a poster upstairs. So one of the problems, showing some of the work we're doing in this, and so one of the problems that can appear here is because you have different modes, a spatial mode corresponding to each core of the fiber, and so you should have some mode dispersion between them. So meaning that the delay that so you send a pulse of light through each core, the delay it feels is different, and it depends on imperfections and so on in the core, and it's like having, it's something that's a statistical thing, right? So it's something like polarization mode dispersion, but it's actually the intercore mode dispersion. So we're in the process of trying to measure this, and for 2 reasons. One is that it's never really been measured before, so we're trying to use actually 2 photon interference to measure it, which would be cool, like a quantum metrology measurement of something real, and that's never been measured before. But also the question is, well, how relevant is this for an experiment? So if I want to do, teleportation, I need to have pulses coming from different places and so on, but now if they're all having different dispersion, different delays and so on, this is going to be a problem. I'm going to have to know how to deal with it. So finally, the idea is once we have all this going, is to do, again, this path entanglement and entanglement-based QKD, steering-based QKD, and so on over the multi-core fiber network. So these are things which are, say, partially ongoing or on the roadmap for the next year or 2. Well, I just want to finish with, say, 2 more things quickly. One is that we always have space for people, so if you're interested in visiting or studying or whatever, we have open positions usually, so you can get in contact with me on email, or I guess this QR code will take you to our webpage. As I mentioned, that we're 3 professors, not just me. So the other thing I wanted to say is just like there's a particular podcast I like of interviews with different people. And so they always ask at the end, well, why do you do what you do? Like, what motivates you? And so I wanted to say, why do I like working in quantum optics and quantum information? Why do I think it's kind of a special field and so on? So the main reason is this, is because, well, I like that you can participate in every aspect of an experiment, right? So you could have an idea, you could say, I have this idea. You could do some calculations. You could see that it's possible. You could do some numerical simulations all yourself, or help your friends can help you, and so on. And then you could go in the lab and do the experiment. So nothing is, it's all, there exist experiments where you can participate in all aspects of it. You can help write the paper, you can help analyze the data, and so on. As opposed to, say, some fields of physics, like in, say, high energy physics, where, okay, I'm either working on the theory, or maybe I'm working on a certain part of a certain detector system that goes in some wing of some gigantic accelerator. This is not like that. So you can really kind of participate in everything, and if you work in a lab, you know that sometimes you don't want to be in the lab, and you say, I'm going to stay home and analyze data, or write a paper, or do some calculations, whatever, which keeps you sane. Sometimes if you're working too much theory, you say, I need to go in the lab, and then so you have this kind of freedom, and I really like that. The other idea is you can say, like, you can have your own idea and go do it. That's like the most rewarding thing there is in science, I think, right? To see your own idea, see clicks that reproduce what you thought would probably happen, right? Yeah, so this is what I wanted to say here. So, of course, the other thing, well, here, I wanted to make a point here with this, this image here. So, who knows who MacGyver is? Okay, good. You're mostly PhD students, I guess, so MacGyver is. When I was a student, I guess a master's student, Paulo Soto Ribeiro came to the lab where I was working. The first impression of Paulo, and he came to the lab. It was in Carlos Monking's lab. Paulo came and he said, oh, I go in all these labs, and there's pictures of Einstein on the wall. He said, my lab, I'm going to put up a poster of MacGyver, because you have to be MacGyver. And that's something that really stuck with me, and you really have to be MacGyver. You really have to, make it work, especially in working in Latin America, Brazil, wherever. It is what it is. You have to make it work. During my master's, the laser broke. So I started doing theory for 7 months. Then the laser got fixed, and then I was able to do the experiment. Or we were trying to do an experiment, and a detector broke. We only had one detector. Okay, what can you do with one detector? How can I detect 2 photons with a single detector? So you find a way and you make it work. So you really have to have that MacGyver mentality, and I think there's kind of different approaches to science. One of them is, okay, I want to do this. What do I need to buy in order to do that? But if you take that approach on a limited budget, you will be waiting forever to do things, and then until you get all the funding necessary, and then probably someone else did it. The other approach is, okay, what do I have? What can I do with this? What's interesting, and so on. So, I think a lot of us learned this lesson over COVID, right? Because everyone who was working in the lab all of a sudden is working from home. So maybe you had some results, and you took advantage, and you analyzed them, or wrote your paper, whatever. But then you had to do something new, and so everyone did theory for a while. But you have to have that flexibility, and I think, and especially in the lab, it's, okay, what can I do now with what I have? How can I push things forward today, Yeah, the other thing I really like about quantum optics, quantum information, is that I really like this idea about how I've read several history books and so on about the development of, computers in the 1950s, 1940s, whatever. We all saw, what's the name of the movie about Alan Turing and the Enigma and everything. We're really that time, right? We're building these things that, someday will probably, be, I don't know, 100 years from now, someone will have a cell phone that's based on, something that was worked on in some quantum physics lab today. So maybe not, The point is that we're working on this something that's real kind of state of the art, and it's clear that this will be part of technologies someday soon, and we'll probably see it you'll definitely see it in your lifetimes, right? So that's pretty exciting, I think, right? Not all areas of physics have that, right? And so that's cool. Okay, that's all I wanted to say. So these are the take-home messages. Yeah, so I hope you're convinced, or you agree with me that photons are an important part of quantum technology, and they will be an important part. So, even if you don't work in photonics, you most likely, if you're working an experiment, will have to know something about light and photonics and all these devices we've been talking about. I'm pretty excited about multi-core fibers, and I think it's going to play. It's going to play a part in telecom, and also probably in quantum communications and so on in the future. And the big thing is, try to have fun and look to do what you like to do and so on. Thanks, and yeah, here's my email. Thanks. I just want to say one thing. So I asked you all if you knew who MacGyver was because I was giving a lecture to some undergrads a few weeks ago, and I said, oh, you have to be like MacGyver, and everyone was, no one knew who MacGyver was, so I wanted to make sure that,
Hi, Steve. I have a question about the implementation of the network. Why, if you work with 7-core or 12 cores multi-core fibers, you installed a 4-core multi?
Why did we install 4-core fiber?
Yes.
Because, well, so in the beginning I mentioned that from the point of view of, say, high dimensions, it's not so interesting to have, many cores, because that means you have to have many detectors. It's the resources necessary grows quite a bit. Also, the company all of the devices we've bought from now, up to now have been 4-core, 7-core. So when we decided, okay, what are we going to install? We installed the 4-core mostly based on what we had, right? We could, in the future, install a larger one and so on. But like the real, I could say the many cores is more interesting if you're going to use each channel separately as a communication channel. So for classical communication, they're working, I think I saw something of like 62 or 1-core fiber. Great. They're, again, it's great for classical. Or if you're trying to do this multiplexing of, say, polarization entanglement in the fiber, I think then it's probably also interesting. But we're more interested in, okay, I want to take single photons and put them, make a superposition of single photon in the different cores. This has kind of been our approach because we're interested in the high dimensional, but not so high, or else we lose, it's not practical.
You said that Bob can cheat the key that he received, but how can you control the key that he really received and the key that he's cheating?
In QKD, in quantum key distribution. Yeah, so Bob isn't, let me just go back to the slide. Yeah, so here in QKD, Bob's not cheating. In principle, Bob and Alice are collaborating amongst each other, right? All of the cheating or the eavesdropping is done here in the middle. So it's someone who's, between Alice and Bob is maybe stealing the qubits, maybe stealing one and replacing with another one. They can do many things. They can try to measure it. They can just, they could just block the channel. There's many different things they could do. But the idea is that A and B are honest and are collaborating with each other. The point is they want to communicate a message to each other, and so they want to establish this key, right? Yeah. So all of the cheating or the eavesdropping, the manipulation is done here in the middle by a third party. Yeah.
Another question? Yes.
Hello.
Hi.
Thank you for the lecture. It was really abarcative. It's said from the point of the theory of quantum information and the physics. And what I usually don't hear so much about is the actual technology, like going commercial. So it's maybe the question is too general, but how do you think that every lab is making systems and choosing their own technologies? How do you think this will mash up in the future, when it goes commercial? For example, I hear more about the photonic chips, and how do you think everything will be integrated at that point? I don't know.
Yeah, I mean, I think everything will be integrated. I think that, I mean, even, you know, say like atomic systems, other solid state systems and so on. Of course, like this is one of the reasons why the photonics is important. So even if, you know, in the future, all of the sources are now, you know, based on atomic systems or whatever, you still have the optical fiber and different techniques, which, you know, we study, which will be in the middle to link these systems. So yeah, there is a lot of work in trying to integrate them together. How do I think they will integrate? I mean, I think I don't know. You know, I think I don't know if anyone knows, but I think there is some work on, say, standardization, right? So there's agencies like ETSI, which is the European Technical and Science Institute, or something like that, OSI, and so on, who actually have put out, say, QKD standards, or standards on different types of quantum technologies. Which right now I think are kind of as guidelines, but the idea is that, okay, let's start to shape, I mean, so, okay, we're gonna do QKD. So there's, you know, 10 different ways you could do QKD, but we want it so that all the different QKD systems all have these kind of characteristics such that they were able to be, you know, so if I buy a QKD system from, I don't know, a certain company, one, and oh, it doesn't work, I'm gonna switch it with company two, that it's gonna work well, right? So, so establishing, you know, like nomenclature, different methods, and so on. This is something that's underway and has been underway for roughly, I don't know, 15 years or so on. So this is something that's really important. You know, how, I mean, it's like, have you ever, you know, the different quantum computers that are available? So IBM has the Qiskit language. I know that Xanadu has Penny Lane. Different companies have their different programming languages, which is, I mean, almost like starting a recipe for disaster, right? You want everyone to kind of start using the same thing, you know? Yeah, so that's, I think, a really important point. And yeah, so what technology and how they will go together, I think that's kind of up in the air still, and I don't know. But what I do kind of, one of the points I was trying to make, and I'll take advantage of your question to make it again, is that, you know, photonics is necessary in all of these systems, right? So even if you have, I mean, even, IonQ, like one of the most promising quantum computing companies with trapped ions, they realized, you know, okay, we can only scale up a trapped ion computer so large until it's just we can't make it any bigger because we can't have, it's impossible to make the qubits on either end communicate, you know, to do a controlled gate or whatever. So what do you do? Okay, I have to have, you know, different modules, and I have to connect them some way. How do you connect them? Through photonics. And then actually IonQ bought a company that specialized in quantum networking because they needed that technology right away. And so I think it's interesting. Photonics in particular is interesting in this regard. It will play a role in something. Thanks.
Great, thank you.
So a final question? No one? No? So let's thank Stephen again.
Thanks.
So I think we can do the closing section.